Okay. Now what is a set of 2 vectors, 3 vectors or any number of vectors is called orthogonal? Each vector is non-zero. Dot product of every 2 vectors is 0. A simple example, see. Let S is equal to 3 vectors x1, x2, x3, where x1 is equal to 1, 2, 2. I am taking column vectors. See, row vectors and column vectors having same procedure, comma, x2 is equal to 2, 1, minus 2, and x3 is equal to 2, minus 2, 1, which implies x1 dot x2. So how to find dot product? 1 into 2, first element plus second element into second element plus third element into third element. That is 2 into minus 2. So plus 2 minus 4, that is 0. x2 dot x3. So in x2 and x3, first element into first element, 2 into 2 plus 4. Second into second element plus 1 into minus 2 is minus 2. Third element into third element, that is minus 2. So answer is 0. And x3 dot x1. So first column into third column or third column into first column. So 2 into 1, 2. Second element into second element, minus 2 into plus 2, minus 4. Third element into third element, that is 1 into 2 plus 2. Answer 0. So therefore, and each is non-zero column. At least one element is non-zero. Dot product of all possible 2 vectors, find dot product. If it is 0, then only that set is called orthogonal. No vector is 0 vector. 2 vectors is 0 implies S is orthogonal set. Okay. Now, the fourth definition is a set S is equal to set x1, comma, x2, so on, xn of n vectors is said to be orthonormal if one, S is orthogonal set, that is dot product of every 2 vectors is 0. 2. Length of each vector is 1. Okay. Now, when do we say that some vectors in a set is called orthonormal? First of all, it should be orthogonal. What is orthogonal set? Just as above explained with an example. Followed by one more condition, length of every vector is 1. I shown you in the previous session before break how to find length of a vector with a small example. Okay. So, that means an orthogonal set need not be orthonormal set, but every orthonormal set is orthogonal. So once again I am explaining. Every orthonormal set must and should be orthogonal set, but the converse need not be true. That is, every orthogonal set may or may not be orthonormal set, because one more condition for orthonormal set, length of each vector is 1. Example, let S is equal to set x1, x2, 2 vectors I am taking, where x1 is equal to 1 by root 2 minus 1 by root 2, which is a 2D row vector. That is 2D means 2-dimensional, 2 elements. And x2 is equal to 1 by root 2 1 by root 2. So here x1 dot x2. So that is 1 by root 2 first element into first element. In this column vectors I considered, in this row vectors I considered, both having same procedure. 1 by root 2 into 1 by root 2 plus minus 1 by root 2 into 1 by root 2. So denominator same, add the numerators, 1 minus 1 becomes 0. And how do you find length? And length of this first vector is equal to square root of 1 by root 2 whole square plus minus 1 by root 2 whole square. So that is square root of 1 by 2 plus 1 by 2, that is 1. Length x2, square root of 1 by root 2 whole square plus 1 by root 2 whole square, that is square root of 1 by 2 plus is equal to 1. So therefore S is orthonormal set. Please write fast. So the only difference is, for these two definitions you have to find length of each vector. If length is not equal to 1, length of any vector is not equal to 1, then that set is orthogonal set, provided dot product is 0. Every two vectors dot product is 0. Now the next one, ninth definition. Today's seventh point is a shortcut method for some standard determinants without expanding, and properties on determinants. Eighth definition is dot product of two vectors length orthogonal. Ninth definition is, already in the break session yesterday some of you asked symmetric, skew symmetric, orthogonal, Hermition. That I am going to discuss now. A square matrix, this is common for all the coming 9 definitions. A is called or is said to be, in this first one, symmetric if A transpose is equal to A. On the other hand, I am writing side by side, Hermitian if A to the power theta is equal to A. So in every definition I am giving pairwise, that is side by side. One is transpose, other is transpose conjugate, that is theta notation, that is explained in the day 1, that is Tuesday. Okay. So here one more operation, conjugate. Generally conjugate will meant for complex numbers. Conjugate of real number is same. So that's why this type of side right hand side matrices are complex matrices example. This side of matrices is real matrices. Okay. So transpose of a matrix means interchanging rows and columns. Conjugate of a matrix means every element is replaced by its conjugate. So whenever satisfying this type of conditions, that is called symmetric as well as here Hermitian. Okay. So simple example, A is equal to A, H, G, B, F, G, F, C. Just you transpose, you will get again same matrix only. Okay. Now how you remember easily? Whatever you are considering first row elements, same will be in first column. Similarly, second row elements, whatever you are considering, put them in second column. So how you identify easily in ABCD options which one of the following is a symmetric matrix? Row elements is equal to corresponding column elements. Then that matrix is symmetric. Okay, without verifying A transpose is equal to A. First row elements is equal to the same in first column elements. Whatever the elements in second row, the same should be in the second column. That is called symmetric. Okay. 2. Skew symmetric matrix if A transpose is equal to minus A. On the other hand, skew Hermitian if A to the power theta is equal to minus A. So in skew symmetric, diagonal elements are 0. This is one logical point, one important point in skew symmetric definition. And another point is determinant of a odd order skew symmetric matrix is 0, whereas for even order, it is non-zero and perfect square. So what is odd order? 3 by 3, 5 by 5, 7 by 7, 1 by 1, etc. What is even order? 2 by 2, 4 cross 4, 6 cross 6, etc. So first of all, it should be skew symmetric. For odd order skew symmetric matrices, if the question is determined without expanding, answer is 0. Telling if it is 4 by 4, 2 by 2 skew symmetric matrix, even order skew symmetric matrix, if the question requires determinant, what is the answer? According to the options, answer is non-zero and is a perfect square. What is perfect square? 9. 9 can be written as 3 square. 4 can be written as 2 square. 16 can be written as 4 square. These are called perfect squares. Okay. See, simple example. But you remember diagonal elements are compulsory 0. If any diagonal element is non-zero in a matrix, that matrix is not skew symmetric. Please keep this point in mind. So example, A is equal to 0, 1, minus 2, minus 1, 0, 3, plus 2, minus 3, 0. And another example, A is equal to 0, 1, minus 1, or 0, 2, minus 2, 0. Okay. So in this first case, det A is equal to, determinant can be expanded by first row or first column, any row, first row. 0 into its cofactor value, not required to calculate. 0 into any number is 0. This is minus 1 into, because this one cofactor symbol is I value 1, j value 2, minus into that element into deleting this column, deleting first row, second column, you will get minor of this one. So that means AD minus BC, 0 minus 6. Next, this element into minus 1 whole power I plus j becomes plus minus 2 into leaving third column first row AD minus BC, that is 3. So how much answer? 0 plus 6 minus 6. Whereas for this 2 by 2 matrix, it is a direct 2 by 2 A, B, C, D determinant AD minus BC. So 4. 4 can be written as 2 square, perfect square. So this is not equal to 0, non-zero, and is a perfect square. So practice many more problems on 3 by 3 determinant. You will get the experience and your fastness also improved. In this third one, orthogonal matrix. If A into A transpose is equal to I is equal to A transpose into A. On the other hand, unitary matrix. If A into just in all the first side transpose, in the second side, other side, alternative side, theta. Just replace transpose by theta is equal to I is equal to A to the power theta into A. This is also can be proved as a matrix is said to be orthogonal. A transpose is equal to A inverse. Here for unitary, you can also prove in alternative way A to the power theta is equal to A inverse. Just transpose of a matrix is equal to inverse of that matrix. Such matrix is called orthogonal. Similarly, the theta to the power of a matrix is equal to inverse of that matrix. That matrix is called unitary matrix. Now, in this, one important point regarding determinant using orthogonal matrix definition. The determinant, very, very important, of an orthogonal matrix is plus or minus is for any orthogonal matrix. If you find determinant, you will get either plus 1 or minus 1. See, example, A is equal to cos theta minus sin theta, cos theta. Okay, and another example, 0, 1, 1, 0. So just you check the above definition, either finding transpose is equal to A inverse condition or A into A transpose. You know how to write A transpose and you know how to matrix multiplication, how to find matrix multiplication, A into A transpose. Okay, so here that A is equal to AD minus BC, that is cos square theta plus sin square theta is equal to 1. Here that A is equal to AD minus BC minus 1. Okay, so just I am verifying here A into A transpose. What is A? 0, 1, 1, 0. What is A transpose? 0, 1, 1, 0. Okay, which is same matrix. First row into first column, 0 into 0 plus 1 into 1, 1. First row into second column, 0 into 1 plus 1 into 0, 0. Now, second row into first column, 1 into 0 plus 0 into 1, that is 0. Second row into second column, 1 into 1 plus 0 into 0, 1. So, this matrix is equal to I. Similarly, you can verify for this matrix also. A into A transpose is equal to, you will get definitely I. And one more important point for the above symmetric and skew symmetric matrix. Every square matrix A is expressed as the sum of symmetric and skew symmetric matrices. Okay, that is A is equal to half into A plus A transpose plus half into A minus A transpose. Okay, so this is always symmetric. This matrix is always skew symmetric. Take any matrix, it is expressed as sum of two matrices. One is symmetric, other one is skew symmetric. Just here, half into A, full A. Half into A transpose minus half into A transpose. Both are cancelled. Finally, which gives A only. This matrix is always symmetric. This matrix is always skew symmetric. When do we say that a matrix is symmetric or skew symmetric? What is the procedure? Find transpose. If it gives the given matrix, that is called symmetric. If it gives minus into given matrix after transposing the given matrix, then the given matrix is called skew symmetric. Okay, so A plus A transpose. Similarly, which is also true for Hermition and skew Hermition. Just T is replaced by theta, you will get alternative definition, alternative result, sum of Hermition and skew Hermition matrices. A plus A transpose is symmetric matrix. Okay, and A minus A transpose is skew symmetric. And here, if A is skew symmetric, this is one mark statement, then A power n, that is A square, A cube, A power 4, etc. is 1. Symmetric if n is even, that is power is even number. 2. If the power is odd number, you will get skew symmetric. That is, first of all, the given matrix is skew symmetric. Then the question is A cube is 4 options ABCD given, symmetric, skew symmetric, neither nor, or both satisfies. Such questions asked. Then use this result. If the power is even number, then that powers of A is symmetric. If the power is odd number, that A power n is skew symmetric, provided A is skew symmetric. Just these two related to symmetric, skew symmetric, 1 mark logical questions or properties. Now in 9th point, the 3 more types of matrices, that is after symmetric, skew symmetric, orthogonal, 3 more definitions in 9th point. This is 4, that is called idempotent, involuntary and nilpotent. Idempotent matrix, MUT means matrix. Okay, if A square is equal to A. Okay, example, A is equal to 1 0 0 0, which implies A square. A square means don't square for every element. The procedure is A into A. Similarly, A cube is after finding A square into A or A into A square. So the matrix multiplied by itself. First row into first column 1, first row into second column 0, second row in, because second row is 0 rows, so which multiplied by first column, second column, you will get again A. Okay. Next, 5th one is involuntary matrix. if A square is equal to I. Example, A is equal to 1, 0, 0, minus 1. From this, A square is equal to A into A is equal to 1, 0, 0, minus 1 multiplied by 1, 0, 0, minus 1. First row into first column, 1. First row into second column, 1 into 0 plus 0 into minus 1, 0. Second row into first column, 0 into 1 plus minus 1 into 0, 0. Second row into second column, 0 into 0 plus minus 1 into minus 1, 1. So, identity matrix. Okay. And the sixth one, nilpotent matrix. If A to the power n is equal to O, O is a null matrix, where n is positive integer or natural number. The least of all such n's exist is called the index of matrix A. So, A is a given matrix. First find A square, A into A. If you do not get 0, then find A cube. If you do not get 0, then find A power 4. Whenever you get A power some positive integer 0, its higher powers also automatically 0. The least of all such powers is called the index of the matrix, provided it should be satisfied A power n is equal to 0. That n is a positive integer. Example C. A is equal to 0, 1, 0, 0. What is A square? A into A. That is 0, 1, 0, 0 multiplied by again 0, 1, 0, 0. So, first row into first column, 0 into 0 plus 1 into 0, 0. First row into second column, 0 into 1 plus 1 into 0, 0. Second row into first column, 0 into 0 plus 0 into 0, 0. Second row into second column, 0 into 1 plus 0 into 0. So, this is null matrix. This O is null matrix. Okay. This O is here null matrix. So, therefore, index, the least of all powers. If A square 0, automatically A cube 0, A power 4 0, etc. So, the least of all such powers is, in this example, n is equal to 2. That 2 is called index. Index is equal to 2. So, this question asked in GATE 2006, given E into F is equal to G, where E is equal to cos theta minus sin theta 0, sin theta cos theta 0, 0, 0, 1, and G is equal to 1, 0, 0, 0, 1, 0, 0, 0, 1. What is matrix F? This question asked in 2006. Solution C. Just observe, this matrix is orthogonal, and like that this entire 3 by 3 matrix you can check which is orthogonal, that is A into E transpose is equal to I. Or one important point you please remember, in any orthogonal matrix, okay, the rows or columns, every 2 rows or every 2 columns dot product is 0. In every orthogonal matrix, dot product of every 2 rows or every 2 columns is 0, and length of each row or each column is 1. That is, dot product of every 2 vectors is 0. Similarly, length of each vector is 1 whenever it is an orthogonal matrix. Okay, this is x1 column, x2 column, x3 column, 3 vectors. Just you can verify x1 dot x2 0, x2 dot x3 0, x3 dot x1 0. Length of each vector, that is square root of first vector column, first column x1, root over cos square theta plus sin square theta plus 0 square, that is 1 only. Okay, so clearly E is orthogonal matrix. Okay, now implies automatically E into E transpose, that you already verified. Okay, E transpose is equal to, I can write En. When it is an orthogonal matrix, transpose is equal to inverse. Now, given E into F is equal to G, this G is clearly identity matrix, 3 by 3 identity matrix. Identity matrix. Okay. Yesterday, I gave some relations, 1 mark statements in 5th formula. A into B is equal to I is equal to B into A. Product of 2 matrices in whatever the manner is equal to identity matrix. One is called the inverse of the other. So, this means F is equal to E inverse. Okay. So, use this here. E transpose is equal to F. Okay. So, therefore, your F is equal to transpose of the E matrix, cos theta sin theta 0 minus sin theta cos theta 0 0 0 1. This is the answer. Yesterday I told you, since A into B is equal to I implies B is equal to A inverse or A is equal to B inverse or both. Just after this, a note point. This is related to next definition, rank of a matrix. That is the last point in the last topic in the matrix algebra. Before that, we have to discuss some note point. Let A be a matrix, which is either square matrix or rectangular matrix. The determinant of an R cross R submatrix of A is called a minor of matrix. See, A is any matrix, either square matrix or rectangular matrix. You know how to find submatrix, deleting rows or columns or both. But here R cross R submatrix means either 1 cross 1 submatrix or 2 cross 2 submatrix or 3 cross 3 submatrix, etc. in a given matrix A. That means square submatrix. In a given matrix A, there are so many square submatrices. Okay? Each determinant, the determinant of each square submatrix is called a minor of a matrix. So a matrix has so many minors depending on